So I will be dealing with the iron making course in this particular semester. So myself, Dr. Trinad, I'm a senior assistant professor in the Department of Metallurgical Engineering. So I have shared the scheme of this particular semester, MTech first semester. So this you can see is iron making course, and I have subject code of SOEM MST 101, and it's a 4 credit course. So you will be having 50 marks for PRE and 50 marks for your end semester. This 50 will be again divided to 25 plus 25, 25 mid, and 25 will be the TA. So that will together will be 50, and this 50 will be the end semester. So before getting into this particular course, I'll just briefly show you what is the content, course content. So we have 5 modules in this particular course. It is module 1, that is the unit 1, which covers the history of iron making process. So how the iron making process actually evolved across the years. So that we will be discussing in the module 1. And what are the various integrated steel plants which are available in India, and what are the various raw materials which we basically use for the iron making process. And lastly, we'll be discussing about the first raw material, that is the coke, and its process, like how you manufacture the coke. So what are the various methods by which we produce the coke? That we will be discussing, followed by some charge calculations we'll be discussing. So this will covers the module 1, and the next module, that is we'll be dealing with the next raw material, that is iron bearing material, where we will be dealing with various agglomeration processes. One is the pelletization, other one is the sintering. Again, in this, we'll be dealing with what are the various raw materials which are required for the pellet making process, its charge calculations, and what are the various reactions which takes place during the pellet process, and what are the various testings we basically do for the pellets before we subject into the blast furnace as an iron bearing material. So we'll be dealing with this topic, and followed by the other famous agglomeration process, that is sintering. So here also again we'll be dealing with what are the various raw materials which we use for the preparation of sinter and the chemical reactions, sinter morphology, and then we'll be dealing with what are the various testings which we do for the sinters, and some charge calculations will be done. So this module 2 and module 1 will cover various raw materials and its processing for iron making. And module 3, so this will describe about, so once you have prepared the raw material for blast furnace iron making process, then we will be discussing about the furnace and its accessories. We'll be discussing about what are the techniques which we follow for the charging of the raw material. Previously, what is the method which they have followed, and currently what kind of method we are following for the charging of the raw material inside the blast furnace. And then we'll be dealing with how to start a blast furnace. There is a technique called blowing in process. It's a step-by-step procedure to start the blast furnace, a newly lined or a shutdown furnace. In both the cases, the procedure is same. So we'll be discussing about that one, and then we'll see some numericals based upon charge calculations, and what are the various reactions which takes place inside the blast furnace, right? And the fourth module, So once we have done the charging and the processing of the iron ore is taking place inside the blast furnace to reduction, and we end up with the product. Okay, after chemical reactions has occurred at various stages inside the blast furnace, so we end up with certain products. So that what are the various products we get uh, through the BF route, both from the top as well as from the bottom, and its end applications that we will be dealing in the module 4, along with what are the various irregularities which we encounter during the blast furnace running. Okay, and how to overcome those irregularities. Okay, so these topics will be dealing with the uh, module 4, and the last module, that is module 5. There we will be dealing with the alternative routes of iron making. So apart from the blast furnace route of iron making process, what are other various methods by which we can produce iron both in solid form or in the liquid form? Okay, through coal-based or gas-based process. So this thing will be covering in the module 5. Okay, so this is the overall content for this particular course. Okay, in this particular semester, right? Uh, so we'll get into the these are the course contents, and these are the textbooks which we need to refer, which you can refer. There's standard textbooks, all are by Indian authors. Okay, so one second. Right, you can see these are the textbooks which you can refer for this particular course. Okay, introduction to modern iron making by Turkadi, iron making and steel making theory and practice by Andhra Amit Chatterjee, principles of blast furnace and making Make Bishwash, and first course in iron and steel making by Professor Deepak Majumdar. So these are some of the standard textbooks. You can refer any of these textbooks for this particular course. Okay. So we'll get into the what is the history of iron making process. So the Stone Age was basically followed by the Bronze Age, which in turn followed by the Iron Age. So despite relative abundance of iron in the nature, but Bronze Age came before Iron Age. Because the fact is that smelting of iron require more fuel and high temperature. So we have abundance amount of iron is available long back itself, but nobody able to realize or recognize this particular metal. So that's why we could not able to recover or extract this metal from its ores. Okay. The first sign of iron was dated back in 4000 BC, and at that time the iron ore smelting was done on a furnace called bloomery. So you can see, so this is half, you see the initial furnace which is used for the preparation of iron. Okay, and in this particular slide, so you need to observe you see what is the height of the furnace and how the charging process is happening, because there is no automation at all, so it is manually it is doing. Okay, and what kind of raw materials they are charging inside this furnace for the preparation of the iron. So these are the things which we need to focus from this particular slide. Okay, so long back, the iron ore smelting was done based upon a furnace called bloomery, where iron ore and charcoal is basically used as a fuel. Okay. And the size of the furnace was nearly around 30 to 60 centimeters in dia, and it is having nearly 50 to 60 centimeters deep, and that is the dimensions of the furnace, and it is constructed with stone and the clay. Okay. So that is how it was actually started with, and the air was forced into the furnace through a system called bellows. Okay, you can see in this particular picture that a lady standing here, and she is pulling one particular stick. Okay, she is trying to pull down, and then she is releasing that particular stick with the thread, which is tied at the other end. So this is called bellow. Okay, so this is called bellow. This particular part is called as a bellow, where you can see when this lady is pulling down this particular stick. Okay, certainly, the opening and closing of this particular system will take place. Okay, and when you release this, so it will be open. When you pull back, it will be uh, closed kind of a system. Okay, so that is how the air used to get pumped into the system, and the fuel, the charcoal, whatever we are using, that is getting burned inside the furnace. So when air comes in contact with the carbon which is present in the charcoal, so the combustion of the charcoal basically takes place, which used to generate the carbon monoxide gas, and the carbon monoxide used to reduce, and when it interacts with the iron, it gets reduced to produce the iron. Okay. So that is what the technique which previously they used to use. So the temperature in the bloomery was nearly high enough to produce iron in the liquid form, because due to that particular the bloomery process, and by using bellows, we could not able to generate enough amount of heat to produce iron in the liquid form. So that's why the iron, whatever used to get reduced in the bloomery, okay, so that is basically in the form of solid form, having some porous structure, and that pores are basically filled up with ash as well as slag which is generated. And once you bring out that solid reduced iron, so people used to heat that. You can see, okay, so this is the spongy reduced iron, okay, which is formed in the bloomery, and once they taken out from that furnace, they used to heat this spongy product, so that the ash and the slag content which get entrapped used to come out. Okay, and that result in the production of almost pure form of iron, that is called as wrought iron. Okay, so the product of you can say the bloomery is the wrought iron, which is very pure form of iron. Okay, so during this process of producing iron in the solid form, the people have realized that there is a very poor yield from that particular furnace. Okay, and they realize that the poor yield is maybe due to because of the short contact time between the gas and the iron bearing material inside the furnace. So to improve the residence time of these gases and the contact time between the gas and the solid, the reducing gas and the solid inside the furnace. So the only way is to increase the solution is to increase the height of the furnace. Okay, so the increased height allowed longer contact time of ore, the reducing gases, and a high recovery of iron was achieved. Right. So initially, you see here the height of the furnace are very less. So due to which, whatever the gases which are generated within the system, those gases easily used to escape. Okay, without proper utilization. So because of which the yield was very poor. Okay, so keeping that in mind, so people slowly started increasing the heights of the furnace so that the residence time of these gases in the furnace will be improved. Another way, the reduction will take place effectively. The contact time will be put between the gas and the solid. So by the 8th century BC, larger bloomeries were constructed in Europe, and furnace approximately of 1 meter tall they have installed, and which is able to produce iron of 150 kg. Okay. In the 9th century, the same again furnace, where again the heights are increased to around this time from 1 meter to 5 meters, and these are able to produce iron of 350 kg. So this is how slowly have started improving the productivity of the furnaces by increasing its height. Okay. In the 13th century, the next development took place in Spanish, where they are focusing on increasing the production rate of the furnace by decreasing the fuel consumptions, okay, which leads to a new method of producing iron. It's called Catalan forge furnace, where we have a water falling system, and there is an inlet for the air to pass through. Okay, so that this air will be pulled down through this particular setup, and compressed or pressurized air will be pumped into the system. Okay, you can see this particular picture. You can see this particular design. If you see, there is something looking like a two-year system what we have today. Okay, so at the good olden days, they used to try to send the pressurized air into the system through this kind of setup. Okay, so this is called the Catalan forge furnace. So they started with bloomery, and they have increased the heights, and they come up with the Catalan forge. And you can see the air bellows. You see, initially we have an air bellows system used to be there. These air bellows are slowly replaced with the falling water device. That is what we have seen in this particular slide. Initially you have bellow kind of system is there, where we have seen here. Okay, this is the bellow kind of a system. This is the bellow. This is the bellows. This bellow system is completely replaced with the water falling system here. When we talk about the Catalan forge process. Okay. This is called as the water falling system is known as a prompt, which where we are forcing um, the air into the furnace. The forced air is sent into the furnace. Okay. And slowly again, the demand of iron in the Europe is increased. Okay, and they have started again increasing the heights of the furnace to meet the requirements. So they come up with another construction, that is the Stukoven furnace. You can see here, this is called Stukoven furnace, where this is the prototype of whatever the furnace currently, the blast furnace, whatever we are seeing. Okay, this is something looks like the Stukoven furnace. The Stukoven furnace is the prototype of the existing furnace system we have today. Okay, so at every stage of iron making process, the iron makers are encountering some problems, and while addressing these problems, they are coming up with some new technologies. They started with bloomery, and they found out that there is very poor yield is there, and they started slowly increasing the heights. Come up with Catalan forge, where the bellows are replaced with water falling system, where they could able to send some pressurized air into the system. Okay, so that we can improve the fuel consumptions. Okay, and then from there again, as the demand is increasing for iron, okay, they come up with another design. Okay, by increasing the sizes of the furnace, they come up with the Stukoven furnace, which is the prototype of today furnace what we are seeing. Okay, which is built with it was built with stone and clay. Okay. So again, you see, fuel what they are using is of charcoal. Okay, so in 1709, for the first time, they have started increasing coke as a fuel in the blast furnace, because you see, when the furnaces are very small, then people are least bothered about the properties, the physical properties of the raw materials, whatever we are using inside the furnace. But as the furnace heights are increasing, then they focused on the quality of the raw material, and it should have good properties like strength and all. Okay, so we all know very well that coal is not having good strength, and its fixed carbon is also very less. Okay, so because when you start increasing the height of the furnace and you are charging the coal from such a long height, then there is a possibility of loss of permeability. So permeability. So that's why they changed the fuel from charcoal to the coke. So till the middle of 19th century, the furnace top was open. So you can see in the previous pictures that everywhere the furnace tops are open, right? It's not closed as now what we are seeing. Okay. So in the middle of 19th century, the furnace tops are open, and the waste gases burns at the top when it comes in contact with atmospheric air. Then people realize that there is enormous amount of heat is getting wasted. So they try to utilize this heat within the furnace itself, so that again we can lower down the fuel consumptions. So that is how they start with come up with bell type of system at the top. Okay, so eventually attempts were made to use this heat of burning gases to preheat the blast air. Invention of a bell hooper arrangement kept the top closed except when the bells are lowered to charge material into the furnace. So previously we used to have bell type of charging system used to be there, where the top is closed, and they'll be having a big bell and a small bell, which alternatively get opened during the charging of the raw material into the blast furnace. In that way, we can avoid the escape of the gases outside the furnace. So we come up with a double well charging system in the year 1883. Hot waste gas from the furnace top were drawn off to preheat the Stauchaker bricks, which in turn heated the blast laker. So whatever the heat which is coming out, that used to be collected and it is sent to the stoves. Okay. So currently the same technique we are following. Here we are sending the off gases into the stoves to heat the checker bricks, so that the air from the ambient atmosphere will enter into the stoves and get preheated, and that preheated air used to be pumped into the blast furnace, okay, with certain pressure. So in 1876, blast furnace is operated with oxygen enrichment of the blast. So in 1877, injection of coal into the blast furnace 2 years is started. So currently we are doing the same thing. Okay, from the top we are adding the solid coke, and from the bottom we are injecting the coal, that is called PCI. We call it pulverized coal injection. We do to lower down the consumptions of the coke. Okay, so this technique is adopted from the year 1877. In 1883, skip hoist was installed, and 1887, for the first time, the agglomerates, utilization of agglomerates is actually started by using pyrite ore. And 1894, the pig casting machine was invented. You can see at the side, you have a pig casting machine here. Okay, so 1906, yeah, so twilight sintering machine is actually invented. In 1912, the preparation of the pellets started. In 1919, the electrostatic precipitation, that is, you are one of the glass casting system. Okay, you have scrubbers, dust catchers, scrubbers, and electrostatic precipitators. So replacement of electrostatic precipitators have started in the year 1919, and in 1950, the running blast furnace is basically quenched. Okay, so everybody has a curiosity that what is happening inside of the blast furnace, because it is we call it a black box, where we basically charge solid from the top and ultimately we get liquid from the bottom. But what is happening inside the blast furnace, nobody have any idea. So people are very curious about what is happening inside the blast furnace at every stage of at every part of the blast furnace. What is happening? How the solid iron is converting into liquid form. So they want to know. So that's why in 1950, Japanese people, they actually quenched the blast furnace by injecting liquid nitrogen through tuyeres, and they bisected the blast furnace and they checked what is happening at different parts of the blast furnace, and that is how actually the internal structures, or the different zones of the blast furnace actually found out through these bisection methods. In 1876 to 1893, water-cooled cinder-notch cooler was introduced. In 1894 to 1904, the overall height of the furnace and head dia is increased, and other auxiliary equipments are basically introduced. In 1905 to 1920, the overall height of the furnace and head dia is increased further by keeping box height constant. In 1921 to 1946, the overall size of the blast furnace has increased. Improvements in the handling and the blending raw material has introduced. Charging operating conditions were improved, along with gas cleaning, slag handling systems, and utilization of this slag. Previously, whatever the slag is generated to the blast furnace iron making process, it is completely get dumped. Okay, or there is landfills, but they slowly started utilizing this slag as a secondary source at different places. In 1947 to 1966, the design improvements done in stoves to increase hot blast temperature, oil injections, auxiliary fuel injections they have done. And in 1978, the first bell top was commissioned with a double hooper and single hooper, and bendless top is basically introduced in the year 1989. Okay, so this is how the evolution has actually taken place across the years. Okay, and last one, that's iron making process. We'll stop it here. In the next class, we'll discuss about some other topics. Thank you all for joining.